Okay, today we're going to actually get into some real calculus, talking about what's called derivatives. And we're going to look at the first part of this. Derivatives, what is it? Finally, it's time to look at the really fun parts of calculus to begin. We get to look at something with the mysterious name of the derivative. If you're still confused about this, what is it called? What is it really? Derivative really is the slope, and we'll go into much more detail about this. But we're really familiar with slope. We've been doing that since our Algebra 1 and geometry days. So derivative equals slope. So what does that mean to say derivative equals slope? Okay, well, let's take a look at this illustration. We can find the slope of the straight line here using our old friend, the slope of rise over run, y2 minus y1 over x2 minus x1. Sometimes you'll see the Greek letter delta to refer to a change. So delta is change in y over change in x here. And for this problem, we could have something like slope is equal to 1.6 minus 0 over 2 minus 0. 1.6 divided by 2 is 0.8. That would be the slope of that line. Now, we're going to talk about what's something called the secant line. The straight line we drew is called a secant line. Okay, it's equal. Okay, it's a line that cuts through a curve at 2 points. The slope of a secant line is the average slope of all the points along the curve between the 2 points of intersection. Now, the secant line is the average slope, but it generally doesn't give a good estimate of the steepness of the curve at any given point. So if I look at an example like this, I've got this curve here, and I've got a line that has a certain slope, and it intersects here and here. Now I could find the slope of that line, and it would approximate what the slope of that curve is, but it's not perfect, right? So it gives the average slope between x equals 1 and x equals 2, okay? So it's a better estimate. Now, here, 1.6 divided by 0.2 divided by 2 minus 1 is equal to 1.4. So the change in y over the change in x, we're getting a better estimate of the slope here. Okay, let's try it one more time. Let's squeeze it even more here. So we could figure out the slope of this curve now is 1.85. So we're getting closer and closer together. Notice that the steepness of the secant line is a much better approximation of the steepness between 2 points. What do you think would happen if we allowed these 2 points to move right on top of each other? Well, it would look something like this. Okay, and that's what we called a tangent line. Now, the tangent line, old definition, a line that touches a curve without crossing it, okay, just kissing the line at one point. Notice something else, something really important. The slope of the tangent line is the slope of the curve at the point where they touch. This new definition of a tangent line has the same slope as the curve at the point of contact. And that is what's going to be the derivative. So, slope of a curve, how do we go about finding the slope of the curve? Well, remember what we just said. The slope of the curve is the same as the slope of the tangent line. Guess what? We know how to find the slope of a line, right? Rise over run, change in y over change in x. Now, let's see what we can do with that. Tweaking the formula a little bit, change in x, remember we can use that delta x, we'll call that h. So now, what do we have? We have change in y over delta x, or change in y over h. Now, our original equation was y equals f of x, okay? Therefore, y1 is f of x1, and y2 is f of x2. So we have two different points, and they're going to get closer and closer together. So we have the change in y, or the change in f of x values, divided by h, and my change in x. Now, x2 is the first x plus that little tiny delta, okay? And delta x is equal to h. So what do we come up with? We come up with this formula. M, which is slope, is equal to f of x plus some tiny little delta minus f of x1 divided by h. And we could change this delta x to that h as well, like we did at the top here. F of x of 1 plus h minus f of x1 divided by h. And that is going to be the slope. Now, what can we do with that? Okay. Now, we could replace x1 with any x, okay? So here is our definition of slope. Now, what can we do with that? Here is where the definition of the derivative comes in. This is one of the most important concepts of calculus. Last but certainly not least, we come to our final step. Remember, for the tangent line, we allowed our 2 points to come together. In other words, we allowed h to approach 0. Our change in x is going to get smaller and smaller until it's approaching 0. We represent it in this way. Slope m is equal to the limit as h approaches 0 of f of x plus h minus f of x divided by h. This equation is called the definition of the derivative. That means it's pretty important, since after all, the entire rest of the semester we're going to do, and then if you're going into calculus next year, it's going to be based on the study of derivatives. So that definition is very important. Let's see how it works. Find the derivative of f of x equals x squared. Using the definition, okay, we're going to call the derivative of f of x, okay, by calling it f prime of x, and the derivative of y is y prime. Okay, that's just standard notation to get used to. So f prime of x is equal to the limit f of x plus h plus minus f of x all divided by h. The limit of that is h approaches 0. Well, what was our function? Our function was x squared. So f of x plus h is going to be x plus h squared minus my f of x, which is just x squared, all divided by h. Well, the limit of that is 0 over 0. But we have to do a little bit more investigating. So we're going to have to factor this. Well, what can we do with x plus h squared? Well, we could FOIL that and come up with x squared plus 2xh plus h squared. Okay, so we FOILed this, and we're going to do then minus x squared, still divided by h. The x squareds cancel out, and we're left with 2xh plus h squared over h. Now we can divide out an h. Okay, factor out an h and divide it out, and we're left with the limit as h approaches 0 of 2x plus h. And as h goes to 0, this is simply going to be 2x. So you've just taken your very first derivative. Okay, so what that means is that the slope of this graph, x squared, at any point along it is going to be 2x. So if I look at the graph of y equals x squared, okay, let's say at x equals 1, f prime of 1 was 2 times 1, which is 2. So my slope at x equals 1 is 2. So here we've got one tangent line at negative 2, and we looked at the one at positive 1. Okay. So f prime of x is 2x, so at x equals negative 2, f prime of -2 is 2 times -2, so -4. So my slope at -2, where it touches in one point. I know it doesn't look quite like that, but touches in one point would be -4, and at x equals 1, it would be a +2. So that's what it means to take a derivative. So you might have some questions. What exactly does the definition of a derivative tell us? The definition of derivative tells us the equation for the slope of that curve. To find the actual slope of the curve, you must plug in then the value for x wherever you are on that function. Will the definition of derivative always factor to get rid of the 0 over 0? Yes, although sometimes the problems require a bit of creativity. We'll start off with some simple ones, but in general, we'll be able to factor that. And are derivatives really important to know for calculus? Yes, all of calculus A, we'll talk about limits and continuity, is based on derivatives. And that's where we're going to end for today. Now we're going to switch over to the in-class worksheet, and we will do that now.